Good morning, everyone, and thank you for attending today's webcast, Autodesk Inventor Stress Analysis Product Overview. Our presenter today is Kevin Bosch. He's an In-CAD Solutions Engineer with Hagerman and Company. We're also joined on the line by Kindred Cooper to help field questions. Kindred is a Solutions Engineer with Hagerman and Company as well. Before we get started, I'll let you know that you're in listening only mode. If you have questions during the presentation, you can type them into the question panel on the right-hand side of your screen, and they'll be addressed throughout by Kindred, and at the end, Kevin will go over some as well. All registrants will receive a follow-up email containing a link for the recording of this presentation, and with that, I'm going to hand things over to Kevin.
Welcome, everyone, and thank you for registering for this webinar. Here's our agenda for today. Our goal today is to review some of the product design challenges and help you understand how Autodesk digital prototyping solutions and portfolio of simulation products can help meet your business challenges. More importantly, we'll dive into learning about the key benefits of Autodesk Inventor Stress Analysis and hear about other products such as Nastran In-CAD and Simulation CFD. Autodesk digital prototyping is an innovative way for you to explore your ideas before they're even built. It's a way for team members to collaborate across disciplines, and it's a way for individuals and companies of all sizes to get great products to market faster than ever before. From concept through design, manufacturing, marketing, and beyond, Autodesk digital prototyping streamlines the product development process from start to finish. As one of the beginning steps of that portfolio, Autodesk Inventor Professional includes stress analysis, dynamic simulation, and frame analysis. A stress analysis can help you find the best design alternatives for a part or assembly. Early in the design development, you can ensure that designs perform satisfactorily under the expected use without breaking or deforming. With dynamic simulation in the assembly environment, the intent is to build a functional mechanism. Dynamic simulation adds to that functional mechanism the dynamic real-world influences of various kinds of loads to create a true kinematic chain. And finally, the frame analysis overview, you're able to understand the structural integrity of a given frame regarding deformation and stresses when subjected to various loading and constraints. These tools are embedded in Autodesk Inventor Professional. By offering this embedded workflow, Autodesk Inventor Stress Analysis streamlines processes, helping you maintain your productivity and eliminate compatibility issues while equipping you with the integrated tool designed for all skill levels that delivers powerful FEA technology while keeping the familiarity, ease of use, integration, and associativity of your CAD system. With regard to ease of use, stress analysis reduces the need for multiple single platform simulation technologies by embedding FEA technology directly into Autodesk Inventor software, enabling its solid and surface modeling capabilities to provide FEA pre- and post-processing. There's a familiar interface and workflow. A single window CAD FEA experience provides the same look, feel, menu, and tree type structure of your CAD system when you develop your FEA model, enabling a workflow conducive to frequent use of simulation for small changes to products that you typically couldn't make before. Integrated with powerful CAD translation tools, this reduces your learning curve, helps you maintain productivity, and eliminate compatibility issues arising from importing CAD models into different FEA platforms. Rapidly explore how design iterations perform without recreating the setup for each modification. And finally, there's true part geometry associativity. Part geometry data is accessed directly through your CAD system and features this true associativity. So you can easily make changes to your model without having to duplicate the work for validation. Explore what-if scenarios easily with full associativity of FEA and CAD data and validate your concepts. Autodesk Inventor Professional Stress Analysis provides two different types of analysis. Static analysis, evaluating structural loads and conditions, and modal analysis that evaluates natural frequency modes, including rigid body movements. The setup for a stress analysis is relatively simple. First, we set our expectations, eliminate the physical behavior using a conceptual model. In the pre-processing step, we define our material and boundary conditions, our loads, our constraints, and specify contact conditions and mesh preferences. In the solving step, we run the simulation to solve the mathematical representation and generate the solution. The part is divided into smaller elements. The solver adds up the individual behaviors of each element, and it predicts the entire physical system by resolving a set of simultaneous algebraic equations. In the post-processing step, we display and evaluate the results. Post-processing is the study of the results of the solution and the improve inputs phase of the process. In conclusion, we look at these results. Do they meet our expectations? If the answer is yes, then our analysis is done. If the answer is no, we can modify the inputs to improve the results. To modify those, we can reduce geometry that's complex. We can remove questionable geometry, tight corners, radii, whatever. We can change loads and constraints, change the analysis type, and so on. The refinement is a highly iterative process. Let me slide over to the Autodesk Inventor software here. And let's see. There we go. What we have here is a airbag from a rail system, and the goal here is to analyze this lifting jig. Can this jig handle this this airbag, pulling it out for maintenance? The airbag itself weighs about 150 pounds or so, a little more. So we want to put this kind of load on it and make sure that that our design is going to be able to handle that load. We're also going to take this just a little bit further and do what's known as a parametric study. How can we make this lighter? How can we make it better? We'll look at some different options for that. So our first step is really to go into the stress analysis environment. And on Inventor's Environments tab, we can select Stress Analysis, and we'll go ahead and create our design study. The first thing that we want to look at, I'm going to just change this name. And I want to change my objective to be a parametric dimension. We're going to change some model parameters here and look at those differences. And also for how our parts are going to be created and the most common type of contact. We've got a few different options here. Now, as far as the model itself is concerned, oftentimes we want to simplify what we're looking at. So we don't necessarily need to look at this entire model. We can come in and choose different design representations if we want to, different levels of detail or positional representations. In this case, I'm actually going to exclude some components right from the study itself. So just over here in the browser, I can come through and select a few items and just simply exclude those. We don't need to calculate those. We don't need to look at those. A few others here, let's see. And our handle, we can exclude those from the study. So we've got that part set up. Typically, our next step would be to go into the materials area and assign our materials. In this particular case, the things that we're going to be looking at already have materials assigned. We see some areas here that that are just using the generic material, we can override that if we so desired, and we can see our list of different materials here. In this case, we're not looking at those, so these are set up pretty well. We can change our material type or our material library if we so desire. We have that ability as well. We need to set our constraints, and this is simply tied down right here at this little lug. We'll go ahead and apply that. And we need to add our load. So we're just going to do a load of basically 780 newtons. That calculates out our mass and gravity. And since we've put it both of these flanges here, that separates that entire load out over both of those areas. Our next step is to actually look at our contacts, how our parts are coming together. And to do this, I'm going to use the automatic contact tool first. Go ahead and let that run through. And that creates a series of bonded contacts for us. Now, it's a pretty comprehensive tool, and oftentimes it will take some things that we don't necessarily need to have. So we can come in and look at some of these contacts and see if we actually need them, and we can kind of see there's a tube here that's got some edges, and we really don't need contacts there, so we can suppress that. I think I've got that set up in the outer clamp as well. Let's see here, there we are. We can pull those out. And then lastly, we've got some fasteners here throughout the setup that actually need to have a different type of contact. So we can spread these out very quickly, select those, and just a simple right click and edit, we can change to a different type of contact. And that is our setup. It's ready to go through. Now, what I'm going to do in our next step is just look at the types of elements that are going to be automatically created in our mesh view. We do have some controls for the size of those elements, or if we need to get in and tighten up elements in a specific area, or maybe spread out elements in a specific area. We have those controls within the software. This meshes out pretty well, so we can leave that one. And we'll go ahead and run the simulation. And in this case, it runs relatively quickly. We do see a couple of warnings that there's some components that could spread off or slide off. We'll take a look, and what the software does is automatic soft spring. You see these probe flags. Let's see, let's go ahead and turn off. Our probes in max, and as we switch our display, maybe we go from von Mises to displacement, maybe we look at the safety factor, we can see where these probes go. We can review stress within a given plane. Relatively simple, nothing terribly complicated about it. As I said, our main goal here is to set up a parametric design or an optimized design. So we have this parametric table, and I'm going to spread this out just a little bit so we can see some things that are being added here. We have some design constraints that we want to look at. Just a simple right click allows me to bring up a menu of these constraints. We'll look at our mass and let's say displacement, and maybe our safety factor. And I want to set some maximum and minimum values. Our maximum displacement, I don't want to go above 0.2 millimeters. Our minimum, I don't want to go below a safety factor of 4. And now I need to look at the model parameters that I want to be able to adjust. So once again, I can go back into my model tree. What we're primarily going to be looking at are these link arms right here. And I'll go ahead and select show parameters for those. And we've got a series of user parameters: the thickness of the link arm, the slot thickness. We'll see a little slot in the arm there. Its width, the number of slots, and their spacing. So we'll set all of these. These are our slots. Kind of looks like a hole there, but we can adjust that with our parameters. We can come in and set either static values that we want to look at. We can adjust and set a range of values if we so desire, and then how many iterations within that range. So my range is 1 to 9, and I want to see 5 iterations within that range. And I'll do one last setting for our slot spacing here. Now, as we look at this, I think I'll change my view. Let's slide this down just a little bit. Let's look at displacement. And if I want, let's say, our number of slots, so the amount of slots that we've got in an arm. If I simply take my little slider here and move it off to the side, you'll note that it says, hey, this is not available. That simply means that this iteration hasn't been calculated yet. Well, I can come right back to simulate, and I've got some options. The default when I've got a setup like this is to run a smart set, basically 10 different configurations that we can look at. I also have the ability to run the exhaustive set, so that full set of configurations, or I can run this one only. And just simply running this one, it takes about as much time as it would for just the initial run. Once again, it's going to pop and show us those little errors, or warnings, I should say. They're not really errors. The model or the software fixes that, but very quickly we can see that it makes that change for us. Now I've got this model completed. I clicked the close button just a little bit too quick. It's going to come up and ask me if I'm sure I want to close this, and no, I do not. There we go. Let's see. Yeah, I've got this one completed. Running that exhaustive set takes a pretty significant amount of time. For this particular setup with my system, it was, I don't know, 20-25 minutes. Obviously that depends on your system, the complexity of your analysis. There's a lot of different factors that go into that. But I can come in here, go back to that parametric study, and once again, just pulling through and looking at different possibilities. I can view the results for those possibilities if I want to, safety factors, so on and so forth. I can pull in my min-max flags. I can actually come in and say, hey, you know what is the least or minimum mass that I can look at, and it will show me what that design is. Not something that I would care for. I might come back and change the count or something to that effect. But we can see all of these things and all of these different possibilities in a relatively quick setup. There are a number of different types of analysis that you can do. Obviously, we talked about the modal analysis. We can copy this and change our loads, maybe add an additional load or reduce that load. We could have come through and added different parameters for our various parts. All of these things can be done. Let me switch back over here just a minute. Another tool, there's oh gracious, almost 100 folks here looking at this. I'm betting that some of you really want to take your analysis a little bit deeper. So Autodesk has provided Nastran In-CAD. It does work directly in the software, much like Inventor Professional does. You can see some of the similarities here on the left, some of the things where Inventor Professional and Nastran line up. On the right, we can see the differences, things like heat transfer, some differences in linear structural as well as nonlinear structural, some post-processing differences. There are quite a few things that Nastran In-CAD can do beyond the capabilities of Inventor Professional. As we look at this kind of in a basic analysis sense, Inventor Professional is primarily about linear static analysis as well as normal modes analysis. Nastran In-CAD certainly can do those, but also we can look at buckling and assess the stability under given loads, examine structures for sudden failure modes caused by comprehensive forces, critical loads and mode shapes, or linear and nonlinear initial stress. We can look at pre-stress static and normal modes. This enables engineers to analyze structures subjected to initial stress and model the effect of the initial stress state under structures' displacement, stresses, and modes. We can look at linear steady state heat transfer using the principles of conduction and convection heat transfer. Engineers can examine designs for equilibrium temperature distribution. We can review composites, providing easy, straightforward handling of complex ply data. We can look at additional modeling contacts. We've seen some of these with Inventor stress analysis. But Nastran In-CAD goes beyond analyzing individual parts. Real-world simulation of assemblies is possible with sophisticated modeling of different kinds of contact interactions, including sliding, friction, and weld contact types. And within basic analysis, we can also look at thermal stress, and this supports the analysis of structures subjected to a thermal load. We can go even deeper in the advanced analysis within Nastran In-CAD, looking at nonlinear static, computes solutions such as large displacement, rotation, large strain, plasticity, hyperelasticity, and creep, nonlinear steady state heat transfers, solves heat transfer problems with nonlinear thermal boundary conditions such as temperature-dependent thermal properties, linear and nonlinear transient response, random response, frequency response, nonlinear transient heat transfer, solving transfer problems with nonlinear thermal boundary conditions, automated impact analysis and drop test. Sophisticated treatment provides realistic and meaningful impact of drop test simulations. The only inputs required are project velocity and acceleration. And then finally, advanced nonlinear materials. The solver captures complex nonlinear phenomena such as plasticity, hyperelasticity, shape memory effects. This enables analysis to model a wide range of materials from metals and shape memory alloys to rubbers and soft tissues. Some of the additional simulation products include CFD, or simulation CFD for fluid flows, mold flow for plastic mold filling, composite analysis and design for various types of materials, as well as building structure analysis. Some of the additional seminars, live seminars that are coming up, Simulation in the Future of Making Things in our San Jose office in September, as well as a couple of simulation live demos in our Atlanta and St. Louis office, September 13th and 20th. You can look for more information on the Hagerman site for those. We've got some additional webinars coming up. CFD for AEC. We'll be looking specifically at hospitals and healthcare facilities and airflow within those structures. FEA, it doesn't have to be difficult. I know that I saw that Martin was going to be on here. I think this is going to involve Nastran In-CAD. That's in September. And then we've got simulation for SolidWorks users in October. For more information, just additional resources, simhub.autodesk.com. It's Simulation TV, and there's a resource center as well as discussion forums, event listings for different webinars and training classes, some additional learning resources, and you certainly have the ability to ask some questions up there. Plenty of different opportunities for training. Hagerman offers classes for Inventor stress analysis as well as Nastran In-CAD, Simulation CFD, and all of the tools have some really interesting tutorials. Great place to start to get your feet wet with these simulation tools. I won't bore you too much longer. We'll be glad to answer some questions here, but if you do have some more questions, if you'd like a personal demonstration or a deeper demonstration, please contact your account manager. You can also contact Martin Craig. He's our simulation business manager. And last but not least, you can reach out to me, but if I win the lottery tomorrow, I'm probably not going to be here. So we'll you know, I just wanted to give you some extra options there. So that is what I have. Kendra, do you have a list of questions there?
Yeah, Kevin, there's only been 2 questions come in so far. The first one I addressed, and it was regarding gravity and when to specify gravity.
Okay.
For the general masses, I kind of answered it in the sense of if you're ever in doubt whether or not gravity has an effect on your results, it's always best practice to specify gravity and the direction. The last question I thought I would leave for you to answer openly, and the question is, can we do FEA analysis on rubber extrusions?
The stress analysis within Inventor, so Inventor stress analysis tool that we're looking at here does not do that. Within Nastran In-CAD, it does handle those nonlinear materials. So it would, we could definitely do that with that tool. They get, our future webinar with that will definitely get into those. I don't know, do I need to add, do you think there's any more that I need to add, Kendra?
There's a lot of materials out there that can be analyzed under a linear condition under a very small limited window. Wood materials would be one. They're linear up to a very small point, and then they quickly become nonlinear and quickly fail. One thing I've always addressed with anyone looking at nonlinear materials is just about every material on the planet is nonlinear beyond a point, including steel. But any rubberized materials, polymers, plastics, all of those are going to be nonlinear, and any results you try to do in Inventor are going to be inaccurate at best because of the nonlinear behavior.
Let's see. That is correct, Mr. Patel. The current tools built within the Inventor software do not provide FEA analysis for the rubber extrusions. That would require the Nastran In-CAD, which is and operates very similarly to simulation or Inventor simulation. The process that you've seen is very similar, but it does have the capability to handle those. And let's see, Mr. Warren.
John,
yeah, go ahead. Go ahead, Kendra.
I was going to ask if I could address his question. John is asking, what about simulation of thin diaphragms, 2/1000 of an inch thick, 1 1/8 inch in diameter? The very fine line you have to walk when you're working with thin-walled parts. A lot of the analysis packages out there approach thin-walled parts very, very carefully. Depends on the loading conditions, the constraint conditions. It's something to look at. We've had a lot of success with thin-walled parts, and then depending on the configuration of the part, if you've got a very thin-walled part or a thin cross-section, yet the overall length of the part is maybe 40 feet and the cross-section is 2 inches by 3 inches, that gets into another realm of very, very complicated analysis, and you have to approach the results very carefully. And that's with pretty much any FEA package out there. So looking at a diaphragm like that, just based on those dimensions, not knowing the other details, I'll go out on a limb and say you should be able to, but obviously it's going to depend on the situation, the loading conditions, and constraining.
Yeah, material types. Yeah, exactly. Let's see. Is it possible to simulate an increasing load until the point of failure to watch the loading of stresses throughout the part? There is some possibility with that. That would be, I believe, more in the dynamic simulation side. I guess the limitation is the limitation would be that it is part specific. Am I right about that, Kendra? Am I saying that correctly?
It is. There's a couple of gotchas you got to kind of watch out for when you're getting into a dynamic loading situation. The dynamic simulation engine or the kinetic engine can help you define those loading points in time, and you can watch that snapshot in time. And John, to answer your question, yes, that is Inventor Pro.
Yes. Any other questions? I'd like to encourage you guys to reach out to us if you're interested in learning more about inventor stress analysis. We do offer those classes. Looks like we've got a few other questions that are coming in here. Let's see. Mark, to answer your question, when looking at the results, what are the planes being referenced to? Example, X distance, there's no UCS for reference. That would be to the assemblies UCS, so let me switch over to Inventor here. Let's see. There we go. While we don't see the UCS in this particular view, there is a UCS, and apparently I've got my symbol turned off, but there is a UCS within this origin plane of X, Y, and Z within the assembly itself. And can force be parameterized? You know what, Kindred? I don't know the answer to that one. Do you?
In Inventor Pro, I do not believe it can. In Nastran, I'm not sure. We'd have to look that up and see if we can find a way to do that.
Yeah, we'll have to check that one out.
I'm gonna bet my salary and say I don't think so in Inventor Pro, but we'll see.
I would say, well, and even just thinking about it, what we can do is copy designs to change that force.
Yeah, creating different design scenarios.
So let's see, once again, regarding tutorials, we've got, there are definitely some tutorials about stress analysis within the tutorial archive. Frame analysis, we see that in there. These don't go quite as deep as our classes do, and obviously with Nastran In-CAD, that has some tutorials as well, but those classes are very, very informative and very helpful. Any other questions at this point?
Looks like that's all of them.
I see someone with a raised hand there. It does look like that's what we see.
Yeah, it looks like that's it, Kevin. But thank you so much for the presentation. It was great. This will conclude our broadcast for now. If you have additional questions, you can simply reply to the confirmation or reminder email you receive from GoToWebinar. We can route those to the appropriate parties, Kevin or Martin or Kindred or whoever you need to go to get those questions answered. There will be a short survey when the session closes down, and we do ask that you take a few moments to fill that out. We would appreciate it. And otherwise, thank you for attending today's webcast, and have a great day, everyone.
Yes, thank you.